The goal of having intelligent computers is a part of both the foundation of artificial intelligence, in the form of the Turing test, and in science fiction. For example, take the computer on Star Trek.
Computer, what's happening? Explosive decompression decks 5 through 14. Sealing off forward sections. Cause? A flaw in the ship's design. Show me. Analysis. No ship structures exist forward of bulkhead 342.
In both cases, you don't interact with these computers through a command line or a search prompt. You have a conversation with them, and the computer remembers what you say. It resolves ambiguities. It asks follow-up questions. And in general, it places your questions in the context of a conversation. This doesn't look a lot like the existing question answering settings that we've talked about before. To answer questions in a conversation, we'll need new datasets, new evaluations, and new models. Let's start with the datasets. I mentioned some of these very briefly in the datasets video, but now we can linger a little bit longer on the specifics of conversational question answering datasets. There are others, but today I want to talk about 4: Qblink, Qblink, Canard, and Coca. Now, you might think that conversational question answering might mean that you get a respite from my quiz bowl fixation, but not so fast. The trivia community is also a source of found data for conversation-like questions. With my former students, we created a data set of questions. These questions start with a sentence to set the context, the lead-in, and then you have to answer 3, usually, questions within that context. Other than the Manchester-style questions and answers, there's nothing special like pyramidality that makes these optimal. I just think they're neat. For example, you have a lead-in that gives a context. Only 21 million units in this system will ever be created. Name this digital payment system whose transactions are recorded on a blockchain. Now, notice that you cannot answer this question just from the literal Q1 here. It depends on the context as stated in the lead-in. There are plenty of cryptocurrencies, more every day, but the 21 million number is unique to Bitcoin. And Bitcoin is the answer to the first question. Then we move on to the next question. It was invented by this person who, according to a dubious Newsweek cover story, is a 64-year-old Japanese-American man living in California. Now, you could probably answer this just from the clues here, but it helps to know that it, in this context, is referring to Bitcoin. Otherwise, you have to do a multi-hop analysis to figure out that this is Bitcoin and it was invented by someone claiming to be Satoshi Nakamoto. Finally, the last question is much easier if you know that Bitcoin is involved with the Silk Road. Or was, anyway. Let's move on to the next dataset, Qblink, question answering in context, which appeared at the same time as our dataset, Qblink, and is notable for introducing emojis in paper titles. 2 of my former students, and Mohit, worked on this Cranfield paradigm dataset, in contrast to the Manchester paradigm dataset Qblink, where the crowd workers play the role of a teacher and an information-seeking student. The teacher gets to see a Wikipedia page, but the student doesn't. They then have a conversation back and forth, and the student tries to figure out as much as possible about the topic, exploring their own interests. And just like the Qblink dataset, you need to do things like resolve co-reference, know the topic of the question, etc. And again, one of the big pluses is that the answers are all anchored in that Wikipedia page, in this case, the Wikipedia page about Daffy Duck. So there's gold evidence that's useful for machine reading techniques. And while Qblink is linked to the Wikipedia pages, there's no guarantee that the evidence is found there. The new challenge here is that you also need to embed the context somehow to answer these questions. One approach would be to just transform the conversational context-specific questions into normal questions that look more like natural questions or squad. So one of my former students had crowd workers rewrite the questions into new questions that didn't require the context anymore. We called this dataset Canard, short for Context Abstraction, Necessary Additional Rewritten Discourse, which is an awkward acronym that, of course, spells out the French word for duck, canard. So let's take a look at this process of rewriting the questions. Each of these questions is transformed into a context-free question. In some cases, this is explicitly stating the topic of the question, Anna in this case, or it's about resolving co-reference from previous questions. And by teaching models how to rewrite these contexts, you can indeed create new questions that don't need this context, but it's not as good as the human rewrites yet, anyway. The final data set I'd like to talk about is Coca, which looks a lot like Qblink. It appeared the next year. But rather than anchoring on a Wikipedia page, it's anchored on a short vignette. Here, it's an 80th birthday party. Like in Qblink, there's a student and a teacher, and the student asks questions of the teacher. But unlike Qblink, there's also a rationale that helps explain why the question has a particular answer. One thing that you'll notice about all of these data sets is that they're not really a true conversation. It's kind of one-sided. And this is one of the things that makes true conversational QA so difficult to evaluate. You need data sets to train models, but to train a model, you need a loss function. And to have a loss function, you need to know if an answer or response more generally is correct given the context of a conversation. For the data sets that we talked about here, the evaluation can look a lot like our evaluations for normal context-free question answering. You just need to give an entity. Then you can use the same metrics that we saw for, say, matching machine reading question answering. Entity equivalence, exact match, span, F1, and so on. But is a conversation just spouting entities? No, of course not. You should be suspicious of that. You can't just have a conversation through cultural references. As we'll talk about in the long-form question answering segment, evaluating longer answers is really hard. So are there ways that you can make the problem easier within a conversational context? Research and dialogue systems typically divide the task into two phases. First, figure out a dialogue act that fits in the context of the conversation, and then give the specific utterance that you should say, that you should generate, that goes to the user, given that dialogue act. So what's a dialogue act in the context of conversational question answering? There are many ways to define them, but here's one example of an ontology of dialogue acts created from real-world conversations by a team from Colorado and SRI. You need to be able to answer a question with yes or no, ask those questions, ask WH questions like, when was your last training session? And because conversation isn't just information exchange, sometimes you need to agree, give an opinion, or just let your conversational partner know that you're still listening. Sometimes lonely, just talking into the void with no one responding to you. What dialogue act does a comment respond to? Leave it down below. That dialogue act scheme was adapted by researchers from Virginia Tech to make it more detailed. Sometimes you need to give an answer with an explanation. Sometimes you need to answer with a follow-up clarification question, or say that you don't know. So now, to do an evaluation, you can make sure that your system can reconstruct the dialogue acts given the context. This turns it into a classification task. Does your predicted dialogue act match the ground truth? This is a much easier problem than actually evaluating long, rambling answers, which we'll talk about with generation in the next video, and it's really hard. But even so, this is not without complexity. These data sets have the interactions between two people where presumably everything went according to plan. But what happens if during evaluation you select a dialogue act that's different from the reference interaction? The thing with conversational question answering is that mistakes are not the end of an interaction. Ideally, a conversational system should recover from it. Let's take a look at the reference conversation here, where the user asks the system what the capital of Georgia is. The system should give an answer, and the user can give a follow-up question. But what happens if the system gets the question wrong? For example, with the wrong interpretation of which Georgia the user is talking about. Well, if the system gives that answer, the user can react in all sorts of ways. Perhaps they realize that they cared about Georgia the country all along. This is probably the most likely outcome if, say, your users come from Mechanical Turk and they're pretending to ask questions. They're not really invested in the task. Perhaps they correct the system. Perhaps they want to get more information. Why did you say Tbilisi? What's Tbilisi? In any event, we need to know how bad it is that the system said Tbilisi. And we can't really do that without testing the system with real users. Maybe it isn't great that we said Tbilisi, but it's much better than saying that the capital of Georgia is Peachtree or Washington. But again, we don't know that this is a near miss because, again, it's not in the reference. It can go in the other direction too. Let's say that we generated the reference data in a way that was quite a bit worse than what an optimal conversation partner would do. Let's say that your system does something much better than the reference. For example, it asks which Georgia you meant. That's even better, but how do you know? Just because you do the conversation a little differently than the reference doesn't mean that it's wrong. In this case, it's much better. So the challenge is to define an evaluation that measures how useful an interaction is, not the answers at individual turns. I suspect that this will need to take the form of human-centered evaluations to actually go down the good path. You need to have people interact with the real system and get them to evaluate how well it works. And we'll see something like that in our next video, where we'll talk about another way of moving beyond single short answers. What happens if the answers themselves are pretty darn long? This is just a single lecture from a course. YouTube likes to show you these videos out of order, but if you go to the course webpage linked below, you can see the lectures in the right order. And you can get resources like homeworks or suggested reading. You can also visit quanta.org if you want to learn about our systems for creating computers that can answer questions, where Quanta stands for question answering is not a trivial activity. If you want to help the channel, provide a big gradient to the algorithm by liking and subscribing.